So yeah, great to be here. Thanks for having me. And yeah, I would like to tell you about a few projects that we did lately. Like this is more of an overview to those things. So it's a joint work. So here you see, here's our theory group in Geneva, Mehul Malik's experimental group in Edinburgh, and then we have theory collaborations from Hannover and Bristol also in this project. So quick outline. So quick outline. So I try to motivate a little bit these high-dimensional systems because this is my main topic here in this project. So I try to motivate why we look at those, and then I will give a brief reminder on this. That what do we mean in entanglement theory if something is like genuinely high-dimensional? So this is known stuff, and then I will go towards what we did actually, and we took these kind of notions to this EPR paradox on steering and to measurements and channels, and okay, then I will just give short outlook in the end. And let me just get started with this high-dimensional systems, so you know, just to set the stage a little bit. So basically, here I have a real line, if you wish, half of it. So it's dimension on this axis, and on the left we have qubits, spins of electrons. You can have, I don't know, polarization of photons, and here on the right-hand side we have continuous variable systems such as position, momentum of a particle. So the thing is that in these two extreme ends, we know rather well how quantum theory works. For example, if you want to talk about entanglement or measurement incompatibility or uncertainty, these two extremes we know okay-ish. But now what we want to look into is here in this project, so systems of something like consisting of like dimension of like 10 or 50 or maybe 100, okay? Where it gets much more complex, but yeah, we want to see what we can find there and why. Well, on the theory side, our main goal maybe is like to find some novel forms of correlations, like you saw already on my outline, that going from entanglement maybe more towards like EPR, and possibly some stronger forms of measurement incompatibility, which recently also has been seen as a resource for many quantum protocols. So that's on the theory side. Then on the applied side, on the other hand, so this is something like a main point for this kind of dimension 50, dimension 100 systems, is that the noise tolerance is, it scales very well with the dimensions. What I mean by noise tolerance, if you look at entanglement, for example, we have 2 qubits. You can put so much noise, you will for sure destroy all the entanglement. But if you have 2 qubits or going further and further, it scales better. And okay, maybe, okay, I know you guys are doing a lot of quantum computing here. So I'm not exactly talking here like having many qubits, but more like systems, if you think like time bins or orbital angular momentum of photons, where we really have many degrees of freedom. It's not just 2 degrees of freedom, tensor with 2, tensor with 2, or something like this, but it's actually many degrees of freedom, like the Hilbert space basis of this single photon in this orbital angular momentum. It can be like 100 dimensional. Good thing is these are easy to control in the lab today. So we can prepare like states with high fidelity of a very high dimension, and the noise tolerance is then the main selling point somehow for the people doing these things. Okay, so basically, if noise tolerance is such a big thing, then we should be somehow clear that there is no bottleneck in our system, that it doesn't somehow reduce to lower dimensional ones, because if it's really the high dimensionality that is the point here, then what if I can simulate my system with using, for example, just qubit or qubit measurements or channels, right? In every protocol, I think here I have a little bit of like an operationalist perspective. I have quantum states, I have channel, I have measurement, right? That's the 3 components. And if one of these somehow reduces my system to, I don't know, qubits or qubits, then it's not genuinely, I don't know, 10 or 50 dimensional as I would like to say.
You're talking about the total dimension, because you could have many qubits. But
exactly. Yes. So I would have basically single particles here, like a single, or like 2 photons, so Alice and Bob, and then there, it won't be like many qubits side to side, but it's the total, yeah, yes, for this kind of degree of freedom. Yes. Okay. So yeah. So basically, let's look a little bit into this this regime. So first of all, what we know already up from entanglement theory, already from the 2000s. Okay, this is from way before, but of course this we all know. Like qubit entanglement, there is nothing. This is just I have 2 degrees of Alice, 2 degrees of Bob, degrees of freedom, or levels if you wish, 0 and 1. They are entangled to each other. But now if I go to so okay, there's nothing high dimensional. It's a qubit. But look at this state here. So this is a qubit times qubit state, okay? But how I can create it is that I entangle the level 0 and 1 of Alice and Bob, okay, with some probability lambda 1. Then I entangle the level 0 and 2, and lastly 1 and 2. So if I would have this state, I would say, yeah, it's qubit, good, it's qubit. It seems to be entangled, but actually I could very easily simulate this kind of a state just by creating qubit entanglement. Yes, please.
What does it mean to simulate a state?
Okay, very good question. So in this case, simulate would simply mean that I would flip a coin between different preparations.
Oh, so
Yeah.
the generation process based on the order.
Exactly. That's a very good point. So this is, yeah. So here the simulation how I look is in that sense that I'm just flipping coins between these states. Yes. Okay. So this kind of approach is known from entanglement theory already from like 2000 by Terhan Horodecki. So basically the idea is this what is called Schmidt number. So it's just, maybe Schmidt rank of pure states. Well, this is just the convex proof extension of that, so mixed states. And basically what Schmidt number asks is how many degrees of freedom have to be entangled. So what I mean, like how many degrees of freedom have to be entangled. So here only 2, 2, and 2. And with that, I could simulate this state. Okay. So the Schmidt number of this would definitely not be 3, because I never have to entangle 3 degrees of freedom in order to create this one. Okay, I can give you the technical definition. It's not very important. What is more important is just to think that, okay, this is one possible protocol of simulating high-dimensional objects with lower dimensional ones. So the technical definition, if you wish, is simply like this, that is this min-max. So I take a mixed state, I look at its pure state decompositions, and from each decomposition, I just record the maximum Schmidt rank. So like in my example here, well, clearly the Schmidt number, I have some specific convex decomposition there using Schmidt rank 2 states. So clearly this Schmidt number is 2 or 1. It could be 1 if I find a better decomposition. Schmidt number 1 is, by the way, it's also the same thing as separability. So this is 1 to 1. Okay, but the technical definition is not that important. What is more important is just to keep in mind that, okay, in the literature, there has been this kind of notion of how to simulate higher dimensional objects with lower dimensional ones. And here, okay, so it was just about entanglement, and this is all known. So what we wanted to then do, we thought to ask that, okay, this steering protocol, this EPR protocol, and see can we see something similar there. So before telling the high dimensionality of this, I'll just remind you of this protocol. So, okay, it's some things of correlation. So I'm only considering Alice and Bob here, so 2 parties, okay? So just type of correlation which is slightly stronger than entanglement, but yet not possibly strong enough for Bell non-locality. So it really sits there in between. Okay, a lot of applications if you wish. I'm happy to tell about them after the talk, like QKD and randomness generation. This, if you ever hear about this, like one-sided device independent QKD and randomness, it's steering. Okay, and other things. So there are 2 reviews, one by Cavalcanti and Skrupchuk, and one by us here on the topic. So if you want to know about the applications, you can check there, or you can just ask me. So I'm happy to tell. But I don't want to go into these details here. What I want to just say is that remind you of this protocol. So what is steering protocol? Maybe you have heard, maybe you haven't. So I'll just explain it on a very basic level. So here I have Alice and Bob. So how the protocol goes is that they share some quantum state. And what we would like to do is we would like to certify that the state is entangled by sort of only looking at Bob's side. Okay, if I only tell you this, they're going to tell me, yeah, sure. If you look at Bob's side, you will only see his side of the state and can't decide anything about entanglement. Good, fair enough. So what we actually do is that Bob will, so there's classical communication between Alice and Bob. So Bob will ask Alice that, could you please perform measurement number 1? Okay, Alice performs that, and there's the corresponding output, say plus to Bob. Now we repeat this kind of procedure many times. So Bob can in principle do tomography on his side, and he would say that, okay, whenever I asked Alice to measure x equal to 1, and she gave me output plus, Bob could reconstruct this sort of conditional states on Alice performing measurement 1, get x equal to 1, getting outcome plus, and then minus and so on. And some rounds Bob asks, okay, please measure measurement 2, Alice maybe gets outcome minus, and then Bob's state is this after the measurement. So now the task is this, that there's only this classical communication between them, and somehow from these like conditional states on Bob's side, Bob should somehow be able to say if the state is entangled or not. So this is like the steering protocol, how it's formulated these days. Of course, if you ask how does this relate to the EPR, let's talk about that later, maybe because this is just, just 2 outcome measurements, 2 of them on analysis side.
This is the same as one-way LOCC.
One-way LOCC is very closely related, yes, because it would be the Bob telling something here, there's an operation here and information coming back, right? So it's very closely related to one-way LOCC. There's just a thing, what is very important here, because one-way LOCC would be Alice makes a measurement and tells the outcome here. But what is very important is that Bob can actually ask which measurement, because otherwise Alice could just be sending these and say, okay, here is +1, -1, there would be no entanglement. So yes, but other than that, it's LOCC one way. Okay, and so here is then the if you want the technical definition. So no need to care about this side yet, because this is just, so this rho AX, so these are these like conditional states on Bob's side, okay? And this is just what they are. So here would be Alice's measurements, Bob does nothing, okay? So what is inside this trace would be basically the post-measurement state, condition that Alice made measurement X and got outcome A. Yeah? And what we do, we trace out Alice. So basically what we're asking, okay, update the state, condition on X and A, and trace Alice out. And this is what Bob is left with. This is his like post-measurement state on Bob's side. Okay, so now comes this after the question mark. So basically we are asking Bob to try to reproduce these changes in his states by this kind of a model. So what is in this model? This PAX, that is just a normalization factor, because you see, this is not a normalized state, this is subnormalized. So this PAX is not even a normalization, so no need to care about that. This part is the interesting part. So basically, if you think about this, physically what this means is that Bob is holding, so look, these are Bob's local states. So Bob is holding some local states, an ensemble of them, and we ask that could Bob reproduce these changes in his state from a local ensemble by just updating the priors according to classical communication AX. Okay, so this is the protocol, like it has been taken as the definition. You could of course say about once again just one simulation protocol how Bob is trying to reproduce these state changes. But actually, it turns out that this definition is exactly what we want, in the sense that if you're talking about entanglement verification. So if I have a separable state here, this model will always exist. It's easy to construct just from that state. And on the other hand, if we have such a model, then there's always a way to prepare it using a separable state. But it's not maybe the state I have in the lab, but with some separable state I can prepare it. So this bears some rather deep connection to separability. But what is here important to note is that this is one side device independent. So what does it mean is that in principle on Alice we do not need a quantum description. I mean, of course, I said that in quantum mechanics, what this rho AX looks like, this quantum description, but in principle, I'm only looking at these states and classical communication. So I'm not trusting what kind of description we have for Alice's measurements. So in this sense, this is one-sided device independent entanglement verification. Yes. And okay, don't be fooled by what I said earlier, that every such assemblage can be prepared with a separable state. Not every entangled state allows steering. So it's not that straightforward. But separable state, no steering, you have entanglement, you have a chance of violating such models. And if you wish, these models are called local hidden state models if you want. That's just, I will not be using that lingo here. Okay, so here's nothing high dimensional. This is entanglement verification. But now, good. Entanglement is Schmidt number 1 versus not Schmidt number 1. So separability is exactly Schmidt number 1. So that is what relates to this protocol. So then we asked, okay, good. So here we verify entanglement. Could we verify Schmidt number? So let's keep the steering setup where Alice is black box, Bob is trusted. So we are just looking at this Bob's conditional state. And basically, so what we want to do as a picture would be something like this. So every point in my picture here is some kind of set of conditional states on Bob. Okay, so it's just this assemblage of states that Bob has. What I would like to do is somehow separate this assemblage from those which can be, so what are these sets here? These are the ones which I can prepare with Schmidt number 1, so with the separable state. Okay. These are the ones I can prepare with Schmidt number 2, 3, and 4. I would go third. These are convex sets. So what I want to do, I just want to build some kind of a weakness, some kind of a hyperplane here. Okay. And if I would trace this hyperplane against my assemblage, then it would tell possibly that, okay, you are on that side. So there would be no model.
Schmidt number is just the number of non-zero Schmidt coefficients.
It's the convex roof extension of that for mixed states. So for pure states, it's that. And then for mixed states, we take the convex roof of that. So basically, for every decomposition of my mixed state into pure ones, I record the highest Schmidt rank in that decomposition, and I minimize that over all decompositions. Yeah, please.
So what point in this space is that one density matrix, or is it a bunch of
exactly? Yes.
for X and A?
Yes. Good question. So exactly. So this one would be it's a bunch of them. So it's all. So Alice makes a certain number of measurements, has a certain number of outcomes. So basically, that will tell how many. So how many X, how many measurements, A, how many inputs. So it's a bunch of them. It's the collection of all post-measurement states on both sides.
And then the Schmidt number is like the max over this bunch, because it could be that's different density matrix.
Yeah, exactly. So basically what it turns, so this Schmidt number would be the Schmidt number of the state that was used to prepare.
With the bipartite.
Yeah, exactly. Yeah, yes, exactly. And then we would like to, just by looking at this, we would like to say something about the bipartite state and the Schmidt number of this state. Yes.
Each point corresponds to density matrices for both states.
Yes, collection of them, exactly. It's a post-measurement, yeah. This is conditional states. Yes.
And there could be several bipartite states, but you want to sort of, like, I guess it should prove that they're for any of them.
Exactly. So this is, so sort of like anything like Schmidt number 2, this set, for example, here, it's all post-measurement assemblages which can be prepared with some Schmidt number 2 state. Yeah. So of course, if I'm here, I'm also here because I just add a dimension. But yeah, I have to optimize over all possible protocols of preparing, which sounds like a big task, but actually it turns out that one can, at least this kind of weaknesses, one can build quite straightforwardly. Okay, I
have another question. Do you know that its sets are not polytops? Because from the theory.
Very good question, because this one, so this one here, we can characterize with STP, so semi-definite programming, and we do not know about the others. So I would think they might be. I mean, in the beginning, when this, like, for example, this basic steering notion was introduced by Weissman and others, it was not clear, was it polytope? But in the end, it turned out that yes, with semi-definite constraints, we can. So it's efficient to solve if some things are steerable or not. But these other problems, we don't know. Would be very interesting to try and figure out. Okay, so basically, this is the setting that we would like to do. This is like the first paper in this bunch of works on these high-dimensional systems. It's just like Schmidt number verification and this semi-device independent protocol. So I'm not going to go into details how to do this because I want to also tell a little bit about a few other topics. But basically, it's in this work we put out last year, which is just about this. We call genuine high-dimensional steering. Okay, why genuine high-dimensional? Because if I prove that I'm on that side, I could not do it with if I only had access to Q-grids or like 3-level correlations. But actually, we also did an experiment on this, which was quite nice. So, Mehul Malik, his group performed the experiment. So, using a photonic platform, so this pixel entanglement, and so what they were able to do was to prove Schmidt number 15 in dimension 31. And I think this may be something that one should just think for a moment. It's quite remarkable that without trusting Alice, okay, these weaknesses we built for this problem and they implemented in the lab really certified that there was no way that these correlations we see are created by just taking 14 levels and entangling them with 14 levels. So from Alice to Bob. So it really, this was 15, and I would imagine we could have pushed it further. Would we have a bit maybe tighter weakness? But this was the highest. In dimension 31, we got to Schmidt number 15. In lower and higher dimensions, we got to a bit lower Schmidt number. And now to compare.
31 is for one part.
Yes, exactly. 31 local dimension, Alice 31 Bob. Exactly. Yes. Okay, so just to compare, if one would do full black box, so Bell inequalities, what has been done for Schmidt number in dimensions 3 to 8 in this paper? Schmidt number 3 was verified, and here for which bit number 4. These were done with photonics. I think one was integrated or both. Yeah, but anyway. So just to compare that, the fact that we do not require Bell violation, but we trust one party's measurements gives us quite a boost in this kind of benchmarking of the devices. Yeah. Okay, so I want to shift from steering to this measurements. But before that, I would like to mention these 2 works from us as well. I mean, I just took like one protocol of trying to simulate with lower dimensional resources my high dimensional state, right? I could take other aspects also of this, like how does the steering protocol look in high dimensions. So if you're interested, we did it in networks, so where we have many states, many nodes. Okay, and also what we did. So in these high dimensional systems, there's one bottleneck, which is sort of fair sampling loophole, which I'm happy to talk about in more detail later. It doesn't appear with qubits, but here it appears, and we managed to overcome that in basic steering settings. Was the first work to do that by basically building binary, so inequalities for steering inequalities for binary measurements. Because usually they want to do like MUBs of high dimension. Yeah. I'm happy to talk about these after the talk if you want to hear about them. Okay, so basically here's what we did in those works. So like I said, there was strong inequality for binary measurements in this one, and okay, we had some activation results in the networks, but this is not the main goal here. I just want to say there are other aspects of high dimensionality already in steering if you wish. I'm not claiming that ours is the only one in any way. Yes, so one can take many approaches. Okay, so this is basically my steering part. So I would like to talk a little bit about measurements and channels also. So if you now any questions about steering, I'm very happy to answer.
Something about how this verification is done.
How this verification would be done. Okay, yes. So how it would be done in the lab. Basically, what we would do is that we take some functional on this rho AX, so some sort of witness. Okay, and we want to maximize the value of that witness based on the assumption that the Schmidt number of the bipartite state was something. Okay.
This functional as an observable that's measured on
Yes,
states, or
exactly.
First doing tomography of the states and then plus it.
The first. So basically, okay, we have a good idea how the assembler should look like that we have in the lab. So we could do tomography, but actually it's enough that we just have some functional. Okay, then it's of course designed for what we think is there, but some functional that we can put upper bounds based on the assumption of the Schmidt number. So basically what we did is that we measure, so pair of MUBs, so mutually unbiased Bayes analysis sign, then noisy singlet state, and then this witness functional will be also a pair of MUBs, because if you see how you have MUBs and a singlet, how these will look like on both sides, they will also look quite much like MUBs. And then I want to maximize some overlaps between that and some observables. Then it's quite, yeah. But okay, to calculate the upper bounds is actually, it's quite tricky, because this kind of like dimension bounded optimization. It's some, I know that there are some hierarchy methods from in like entanglement theory and Bell locality, but yeah, it took a while for us to find a good witness for this. Yeah. But,
so
yeah.
why, like the reason it's, even though the dimension is 31, you get only 15?
Because of noise is one reason. Yes, another reason is maybe we could have a witness which is a bit tighter. So it can be that our witness is not exactly cutting the line, but it's shifted. Yeah, that's
so like in an ideal experiment, if there was no noise, then it should be 31.
It should be 31. Yes, yes. I think even with this witness, it could be. But okay, the thing is, of course, the noise. So one thing one could do is just try to add more MUVs. So measure more than 2, and of course, then should be easier and easier to show higher. Okay, good. So then I would like to shift a little bit the topic. It's still very similar, at least mathematically, but for measurements. So basically, I said now that, okay, this protocol, how I try to simulate, how I try to verify my Schmidt number in steering setup. That was one notion of high dimensionality. But now for measurements, we can also do such a thing. And actually, it turns out this is the direct translation of the steering part, but it will not look at all anything like steering when I give you this picture. So what do I have in this diagram? So first, the left-hand side of the equality sign. I just have some set of measurements or some set of POVMs, okay? And I have some state coming in, I collect statistics. And now my question is, so this is some D-dimensional system. Could I somehow simulate this by using lower dimensional measurements? So how I would do that, this is once again, this is just one simulation protocol, but how we define it is like this. Okay, take your state, then do some operation, which only leaves you a lower dimensional cut of the state, some C in Cn, but it also gives you a classical label. I mean, this could simply be like a state update in a measurement, for example. But in general, this would be what is called quantum instrument or just quantum operations, because it gives quantum output and classical. Now I ask that on this remaining quantum output, which is in a lower dimensional space, could I, by using this classical information, could I make some other measurements, so these are lower dimensional measurements, so that this whole box would give the same statistics as this one, right? So basically what I do, you send me a quantum state, I filter it to some lower dimensional subspace, and then I remember which subspace I put it into, it's the lambda, and then there I perform a measurement. Right, so it's not that I'm just filtering like always in the same basis or something like this. It's just that I have the ability to have this lambda to say that, okay, it's in that subspace now it's in this one or there. So
this important point of this first measurement or this instrument is that it does not depend on this on X.
Exactly. That's exactly, because if it would depend, we would have much more freedom, and it could be that we could simulate.
Basically, this first step is the most general thing you can do to squash it down.
Exactly. Without keeping X in mind. Then only afterwards, so I store it somewhere to lower dimensional system, and then I'm asked the question. Yeah. Yes, please.
Show that the right-hand side picture is not possible if you want to show that the measurement needs high dimension.
Exactly. So So if this is possible, then I would say that, okay, the measurements actually, they seem to be, I don't know, qubit. Or I could get my statistics by using only qubit or qubit or so measurements. Yes.
This equality sign there, and it was maybe a little bit misleading.
Yeah, there should be a question mark here. Yes, exactly. So this is the question I ask. I want to have statistics. I want to find this model, but it is not possible always. Yes. Yes. So this would be the question. So this is the model we took to simulate measurements, and why we think this might be a good model is, okay, first of all, if n is 1, so what is this? So then n is 1, so here is 1. So what it means, this box here does not give me anything quantum. It only gives me classical output. And what is this? Then this is a one-dimensional measurement, so it's just a probability distribution. So what does this correspond to? We would have here a set of measurements, but here we would only have one quantum measurement, and then we would have, okay, then we would post-process the data of that measurement. So this would actually, this is what is called in quantum measurement theory, the notion of joint measurability. So it asks that, okay, I give you a bunch of measurements. Could you perform them by actually just performing one measurement and just classically relabeling or post-processing this? So this is also, by the way, a topic, if you want. This joint measurability, we also wrote a review, a colloquium review a while back. So it's soon to be published in Remorphus, accepted. And also, if we want to know joint measurements, I'm very happy to discuss, but yeah, this joint measurability is a very central notion in measurement theory, because of course we know from our basic lectures like we have uncertainty relations for Hermitian observables, and then we are always given this intuition, it means that one measurement disturbs the other, or they can be jointly measured like at the same time. But actually Heisenberg uncertainty does not tell us that, it just tells about variances. So if one goes and analyzes this problem operationally, and especially goes to POVMs, this notion of simultaneous measurability, this is the one that one always ends up with, as sort of like a divider between having something more classical or quantum, whereas in states it's entanglement, separability, or coherence, non-coherence. So in measurements it's joint measurability. That is, yeah. So also the point is, so joint measurability. So now what we would like to do here. Okay, so basically what we did, so we took this model, and we built some witnesses for this and some models, like some simulation models, explicit ones. But actually, where one could go with this is what I said to you earlier, that this mathematically is absolutely equivalent to this high-dimensional steering, although it doesn't look like anything like that, because in steering I have two parties, here I have one party. But actually, these measurements here they relate very closely to these post-measurement states in this steering protocol. And basically these channels here, they would sort of relate to the state. So it would be just a joy picture of this would be the steering setup. But now, what is also nice here, so this joint measurability connection, joint measurements here, a bunch of papers from us and from the Geneva group before I was there, where this notion of joint measurability was connected to different types of correlations in a one-to-one manner. So there's like, for example, steering and joint measurements, they're really one-to-one connected. Like one problem, if you can solve one, you can solve the other and vice versa. Same happens for some cases of preparation contextuality and macrorealism. To give a few examples, also in the case of state discrimination, there are protocols where this joint measurability is really a dividing line. Also in thermodynamics, we found protocols where this, and this little one-to-one, it's not something like, okay, I need entanglement to violate steering inequality. It's like, if I have incompatibility, there always exists some state, even the slightest amount of incompatibility is enough to violate this criteria. So hence, what we want to do is actually to build this kind of connection, is built in this paper to see that how, once again, correlations and measurement theory, they really go hand in hand. So far, I haven't told any applications. I'm just giving you definition. You're mathematically nice. It connects to some other things. So we are a little bit with this one. We are a little bit still asking about possible applications, and definitely one possible application would be in randomness generation, or even if I would be lucky to go even all the way to QKD. Of course, if I'm going to randomness, I can check if I would make a key. But I mean, to give the short version of this. I mean, if my measurements are on a qubit, then there's so much randomness I can get out from a qubit measurement. So if they're effectively qubit, I can't get more randomness than some function of dimension. If they're effectively qubit or more, then there is the chance that we get more. So basically, if I would have measurements in high dimensions, which are essentially qubits or qubits, they might not be that good for randomness or QKD. So basically, the point is like this also, that if you only look at the case of n equal to 1, so joint measurement, those are scenarios where we can't get any randomness because it would be only one measurement that would simulate everything we have. So there's no chance for it. So this would be, but this is still very new. So I'm just saying that this is like, we still are looking into this and we want to find applications and modifications. We put out a few already, and but I would be very happy also to discuss it. Yeah.
So the point is this randomness generation is that you don't trust your experiment?
Yes, so I would not trust whatever happens here in the box. So I only trust up to the state preparation, but then afterwards I don't have to trust what happens. Yeah, that's also the steering link, right? So I said that, okay, in steering I trust the assemblers, but I don't trust what Alice is doing on the state. Here I would trust whatever states I'm bombing my measurements with, but I would not trust what the measurement does. I would only collect statistics. So this would be a prepare and measure version, and then the steering would be the entanglement-based version. But they really go hand in hand. So if I can say something about one, then yeah. So basically, there are these steering-based protocols for randomness generation. In Geneva group, I was not involved, but they actually it's pretty much like this with n equal to 1. But this randomness generation and QKD protocol for steering, how they look then in prepare and measure scenarios. It's just joy picture. It's simple as that.
Is there some evidence that you will get more randomness out of tricks than
I think so. There's some dimension. There's some function of the dimension that bounds how much randomness one can get from qubits or qubits. So at least in one paper by Daniel Cavalcanti and Paul Skripczyk, there is this. I think it's called some. It's like steering-based randomness. The paper is about that, and I think they put this kind of a bound with this dimension related. Exactly. So more, yeah, higher dimension, more randomness. Okay, so this is basically, I just wanted to like highlight that this can be done for measurements, and at the moment with measurements we would really like to like find out more applications. But many times it's so that with measurements, the math is easy. Yeah, we don't. At least for me, I'm coming from a measurement perspective, and then from there one can find applications and translate these other settings. Okay, then channels. Last part, channels. So I said now, okay, we have some notion of like simulating with lower dimensional resources, these steering setups and measurements, but also, of course, channels in between. So what to do there? This is still work in progress. So I'm just going to give a brief what we are planning. So one way of maybe, so I could now ask, right, that what is the notion of high dimensionality for a channel in some sense, right? So one way would be that I would ask how well it preserves coherences. Okay, so if it just projects to some subspaces, that's all it does. Well, then it would not be genuinely high dimensional. Okay, so how we do this? This is not from us. This definition I'm going to give. This is from Krusinski and Kosakowski. So okay, we take Krauss decomposition for channel. Okay, this is not unique. And then we ask. So the notion is that what is like preserved coherence? So for each Krauss operator here, one possible way would be that it's the rank, the operator rank. Because if I have a Q3 to Q3 channel, but all Krauss operators are rank 2, we said, okay, but then I could actually simulate the effect of this channel just by sending qubit messages, but between different subspaces, possibly even overlapping ones. This would be one way of defining a low-dimensional simulation model for a channel. And what these Krauss operators are, they can just be, it could be just a measurement, right? Which always projects a two-dimensional subspace, and then in the end we just sum over k, so we forget about the outcome as the channel. So this is one possible way. So basically, this is then the definition. I wasn't aware of this before, but apparently one can, before this process, but apparently one can also define like Schmidt number of channels, and it's a total analog of Schmidt number of states. So basically, what we do, we pick some Krauss decomposition for the channel, and from that decomposition, we record the highest rank among the Krauss operators, and we minimize this number over all Krauss decompositions.
It's the same as looking at the Schmidt number of the choice.
It's exactly that. It's exactly that. Yes. So this is the point. So if I take the Choi matrix of this, it's the Schmidt number of it. Nice thing is that it has this kind of rather different interpretation when it's only a channel, when I'm only in prepare and measure scenario, for example.
So like if your channel was just a big unitary, then it should have like maximal.
Exactly. Yeah. Because then I couldn't create that by just cutting some subspace out. And, yeah. And if it was something like informationally complete measurement where this channel comes from, it would be the other extreme, right? Because it would destroy, like, yeah, it would be basically prepare and measure. So it would destroy entanglement.
I see the node operators are just one point.
Yes, exactly. So entanglement breaking channels have Schmidt number 1. So prepare and measure and prepare channels have Schmidt number 1. And then unitaries, isometries, they have the maximum. Okay, so basically, I just want to say that this is something we are doing at the moment. So we want to go a little bit beyond, because this was just defined in these earlier papers in a totally device dependent way. So we realized that, okay, what we did with steering and these measurements, because actually that connection there goes through the Choi map. So we realized that, okay, good, so maybe we can actually put some bounds on this, but in a semi-device independent manner. So what does it mean, semi-device independent to the channel? Well, it would mean that the same as with measurements, I trust the states I send into my channel, but I do not trust what happens after that. So I will only get statistics. And from those statistics, I try to say something about my channel. Okay, you might tell to me, okay, but come on, this is just a straightforward low-hanging fruit that you are doing from, you know, what you did already. But actually, we are having some experimental considerations with the group of Mehul Malik, because what they do in this, especially with orbital angular momentum and pixel entanglement and their systems, how they transport them, one way is to use multimorph fibers. And those things are quite tricky to describe, especially if I have something like 100-dimensional system. It's quite tricky. We don't have like really, we have descriptions for them, but when I talk with experimenters, we try to see what actually happens in the fiber. It's not that clear. So maybe these kind of benchmarking quantities could be nice, that one could say, okay, even though if I don't know exactly, I can do like complete process tomography. I can at least say that, okay, after 1 meter, after 10 meters of the fiber, I still have some high dimensionality left. So basically, if I would use this fiber on one end of 2 particles used on one end, maybe or 2 ends, I would know that the Schmidt number of the state is still high and the noise tolerance would be high. So this would be the benchmarking, one benchmarking way for this multimorph fibers. So this is more, our motivation here is more experimental actually than physical.
So I'm still a bit confused about this rank, why it makes sense, because I mean, so I imagine there could be, if say the rank is 2, you just have 2 Krauss operators, but you sum them, they could act on different subspaces. So somehow like it still feels like I mean, say if they act on a three-dimensional space, then the whole thing should still be three-dimensional.
Yes, exactly. So yeah, right, that could happen, right? The subspaces could overlap by quite a lot also, yeah? But basically, so then what we would say that fair enough, but in order to create this channel, it would be enough in principle just to say that, okay, with some probability, so basically I can calculate from here the probability, I will just take certain subspace and send the information from that to certain other subspace. Then on another occasion, I take maybe an overlapping subspace and send to another maybe overlapping subspace the information. But basically, in the end, if I sum over all these operations, okay, I would get my channel, but the channel would have been realized by just sending quantum information between lower dimensional subspaces.
So you're saying I should just look at the difference across decomposition.
Exactly. I optimize over all of them and I find them optimal. But even then, I mean, the nice thing about this is that it actually takes into account the possibility of this kind of overlapping in this, like, it doesn't have to be like direct sum that now send from this block to and then that block and so on. So it can really take into account this kind of overlaps.
Yeah.
It looks slightly more complicated. Yeah. Also, I struggled for a while to to really get the like how it looks. But if one thinks about a few realizations of a channel, like for example the measure and prepare, okay, then it's clear it's rank 1, so I'm just sending always some one-dimensional message. Or then if I think about a measurement of rank 2 POVM, or maybe if I couple my system to an environment measure something there, just looking at the instruments, for example, I got from measurement process, this in the end would be just summing over the outcomes, so forgetting about the outcomes. So everything could be done with just two-dimensional interactions, possibly. But yeah, it is. I'm not saying that it's a very intuitive concept. Something like capacity of channel might be much more intuitive, but much harder to calculate, possibly. So yeah, but for this we can find witnesses which are just prepare and measure. So yeah, this is now one benchmark that we are trying to work with and see a little bit what it actually means. Yeah. Okay, good. So then I'm already at the point that I think I can just wrap up. So so what we did, so there are a few papers here, and so these were the new concepts somehow that we defined. We took the Schmidt number and we played around it with steering, incompatibility, measurements, and then channels. The channels is still a work in progress. So on steering, yes, we did the experimental test there, so we got the Schmidt number 15 out of this semi-device independent setting. And okay, measurements, potential applications would be nice. So the randomness clearly seems like one, but also one direction we want to look into is really like build a more rigid connection between already in the case n equal to 1 and randomness and maybe even QKD. Okay, channels, we have this upcoming work. But maybe more interesting is telling what we did, because is maybe to think about what could be there to be done better, because these were now just first works on these topics basically. So the witnesses we are still trying to find. Good question was, is it an STP? Yeah, we don't know. Maybe it is, or maybe we can at least find some outer approximations with STPs and find better witnesses. Would be interesting for benchmarking also in the lab, not only theoretically. One direction would be this continuous variable generalization of this. This is rather involved. I've worked a bit on it, but these kind of concepts of Schmidt number, they become really tricky. So I can tell you later if you want, but they become tricky. So one has to be very careful. Also, then one has continuous POVMs, so one gets. So the Schmidt number problem comes from topology, and then of course one continuous measurements. Then you have to take measure theory into account. So there are certain caveats. But okay, I think we can do it, but it takes a little bit more work. And okay, one thing that one could try to do is sort of unify the picture. If one gets this continuous variable stuff done, we have channels, steering, and measurements. So put everything under one umbrella. See where do these connections work and where do they break down? Some of them will break down already in infinite dimensions. One doesn't even need anything continuous. That will be more of a math problem. But yeah, with that, that's my last slide, I think. Yes, I would like to thank you for the attention.
Can you maybe go back to the beginning? I think you had some, like at the beginning, you had some overview of like what is the advantage of having
here, this one maybe. Yeah, yes.
Because isn't like, yeah, you mentioned it, noise tolerant protocol. Shouldn't that be an application as well? But you mentioned randomness.
Yeah, exactly. Random.
But
Yeah.
somehow like being able to demonstrate that you had better error correction. So that would be cool. Huh?
Yes, that would be of course very nice. So yeah, exactly. So randomness. Yeah, we thought that's just from the point of view of measurements, but indeed when you high dimensions, like because we have channels, measurements, and correlations. So indeed this noise tolerance, and it is quite, it's really high, the noise tolerance. Like if I look at steering, this work that I just mentioned in passing, this loophole, closing the loophole, it's actually one is very short measurement times when one has high dimension to get already up many standard deviations, violation of the steering inequalities, and the noise tolerance and loss tolerance is high. But indeed, that would be interesting.
But so that, are you saying you already seeing it, kind of interpreting?
Noise tolerance we can see, but it's just steering experiments. So what I mean just is that there would be for sure many others. Like for example, I know, so in computation I've seen some works where people say that, okay, for channels, for example, if I would just use higher dimensional channels, the capacity is much better. So I can sort of like do easier some tasks if I just allow for Qgrid or higher dimensional channels.
I'm actually wondering, so like how meaningful are these Schmidt numbers actually? Because, you know, as a like if you have just states, let's say, then, you know, as a measure of entanglement, it's very, it's not robust because you would have, like, let's say you have a pure state that has many small Schmidt coefficients and then one very big Schmidt coefficient. Then it's like you can make this arbitrarily close to the product state.
Yes.
So like you could in principle have a Schmidt number that's very big, but then the state is like this.
Yes, exactly.
So how does that, because, you know, you were kind of saying that like when you have this optical fiber, you could just like, you know, stamp on it like, you know, Schmidt number, you know, 100 and sell it for 111. 75. So like yeah, does it actually mean something?
Yes, very good point. So now I concentrate on Schmidt number. So okay, first of all, Schmidt rank works exactly like that. Yeah, I can get like arbitrarily close to a separable state and have a high Schmidt rank. Schmidt number is a little bit better, maybe in the sense that it's searching for all possible recompositions into pure state. But actually, so what we did, so now I want to talk about Schmidt number, but we also, there's also what is called Schmidt measure. So Schmidt number, I'll just show you the definition. So jumping with my slides, but so, because here indeed, because we take this min max, but actually all these definitions also work for what is called Schmidt measure. So Schmidt measure would counter a little bit to like this kind of that, okay, I'm very close to some separable state by the fact that it would not be max. But I would here actually take, instead of the max, I would take these priors into account. So I would take the average Schmidt rank. And then it at least, so I agree with pure states, it is problematic. But now, if I'm a mixed state, then that's the kind of example that's very close already to a product state. The fact is that this, okay, then I can find convex decompositions where there's a lot of weight on the product state and hence it evens. But it is a good point. So we did that also, I didn't mention it here, but Thomas Cope, we did this Schmidt measure also. But then it's also getting hard to calculate. So then trade-off.
But can you have also weaknesses for that?
Yes, in some cases one can, indeed. And also in the channel work, I think we are gonna try and witness those for the 5%.
Or is it that basically you have maybe some kind of prior that you expect your state not to be in this like kind of pathological regime? Like, because, yeah, I guess I'm just wondering if you, when you certify with some experiment that this Schmidt number is big, I mean, it doesn't certify that you are not in this pathological class. It could be that you have like a pure state that is, yeah, it's still very.
Yes. So this is a good question. This is also something we have been thinking about a lot. That where are the pathological cases? Where do they lie? It is a tricky notion because one has to optimize over all convex decompositions into pure states. Okay, the easy way out would be to say, okay, at least in the experiment, it's never pure. So in that sense, one could say that no matter how much we push it, it's in the pure. It won't hit the pure state pathological region. But now the question is, are there these kind of regions for mixed states? Right. So how does this this inclusion? They are all convex sets, but how how do they actually look like? This, of course, is a hard question. Yes, but I haven't come across an example of Schmidt number where this kind of thing, when it's really a big state.
But if you would do tomography, you would see that the state is not so much.
Yes, yeah. In experiments, typically, this would be the case.
So, like, is the advantage of using a Schmidt number that somehow it is like the semi-device independent, as opposed to if you would be doing some other way to certify that it's. So here we can do. So the thing is with the steering setup, we were thinking for a long time that. So what we certify with that is entanglement. So Schmidt number 1, or incompatibility of the other parties' measurements. That's how we certify. But we're thinking for a long time, is this really all? So now we just took that and put it to a steering setup. So the advantage, I don't know, it's an advantage that it can be certified SDI, but we don't know other quantifiers of dimensionality which we could. So basically we took it because that we thought, okay, it's a reasonable measure, and yeah, it fits. So we can develop techniques from just the steering setup to certify it. So, yeah. Okay. Are there any other questions?
Did you consider some multipartite setting?
Oh, this is a very good question. So I did. What we are doing at the moment, I didn't mention here, we do multipartite, but we do in a network. So we can certify this kind of Schmidt numbers and measures in a network, but then it's only bipartite, like network where we have bipartite sources. Now, if you want to go to real multipartite, like 3-party case, the thing is the Schmidt rank itself already. So it's sort of a tensor rank. So when I have 2 parties, it's nice, it's a number. When I have 3 parties, the tensor is 3-dimensional. So the tensor rank is not a single number anymore. So that takes all directions into account. It's getting trickier. So there's a paper by Markus Huber, I think Martti Peranno, possibly with a few other guys, who consider Schmidt number for multipartite settings. And I discussed with them, could we do the steering one, but somehow it seems like we would need to sit down for quite a while to do it. There are also other approaches to Schmidt rank in these settings, but the tensor rank based seems tricky.